Hey, Dr. B here, and let's have a look at taxol, also known as paclitaxel. This has a variety of uses. It can be used for the treatment of breast cancer, lung cancer, ovarian cancer, as well as Kaposi sarcoma, which can show up as a byproduct of HIV. Here's the structure here. Notice the severe complexity of the structure. All sorts of chiral centers. Decent water solubility, I see two OHs and an NH. But wow, what a complex molecule. Look at all those fused rings there. 1, 2, 3, 4 in a row right there. This was discovered in 1971 as a natural products assay hit, where back then they oftentimes took all sorts of natural products and tested them against various assays, tested them in assays against some sort of disease, for example. And from this lead in 1992, 21 years later, it got FDA approval. Being a natural product, it must have a source, and it comes from the Pacific yew tree, which I guess looks like that. And there's some beautiful botanical art there. The mechanism of action is that it inhibits microtubule formation, which is something that cancer cells do, so this helps prevent cancer cell division. That's a good thing. Now, it was initially sourced naturally, but once it became popularized, they needed a lot of it, and so it's now produced semi-synthetically, which can be a green way of making things. You don't have to start from scratch. I mean, in 4 steps from this substance here, which can be obtained from other natural sources, you can synthesize this. But it's not an easy thing to do, since you have to maintain the chiral centers, which means that, for example, do you see how this acetyl group is coming out of the plane of the board? If you did a type of reaction that inverted that stereochemistry, well, that's just no good. You have to maintain not only the chemistry absolute, but just the stereochemistry, the ups and downs. And so they do that typically through the use of chiral auxiliaries, which in a way is just getting something else in the way so it has no choice except to react on the side that you want. So if you have a substrate here, but you just want to get the chiral product here, which might be either wedged or hatched, you might want to put a chiral auxiliary represented here as X sub C right there. And this would probably have some favorable topology. So for example, perhaps it's just huge on one side but not the other, all the way over to this region here, so that when you then react this substance, it can only do so on one side. That's the idea of a chiral auxiliary. Hey, if you want to learn more about taxol, and I think you should, there's 2 great articles that I've added here. Taxol's Next Stand, which dates all the way back to 2001, which is a financial look at taxol, but it includes a surprising amount of theory as well as a more recent research paper from 2015 that talks about how they're trying to change its structure to treat ovarian cancer, because from what I understand, there's a host of undesirable side effects associated with this substance. And so the so-called taxanes meaning do an SAR study, a structure-activity relationship on this, and try to dial out the bad effects and maximize the good, have been, as far as I can tell, largely unsuccessful. So there's some suggested reading for you, and this topic is taxol.